Maybe when we have choose a mode, so you say volume control mode, Matthieu, what kind of volume should we use for a patient? And maybe the first question will be, do you think that volotrauma is a real entity, or it's something just for really severe ERDS patient or physician in the lab with rats and pigs?
Well, sure. Thank you very much for the question. I guess the main entity would be ventilator-induced lung injury, of which high tidal volumes would be a great contributor. It has been obvious, in fact, from experimental studies in rats, especially from Didier Dreyfus and others, that using high tidal volumes would lead to structural and structural consequences for the alveoli, with epithelial injury, endothelial injury, inflammatory response that would mimic ARDS indeed, and also biological alterations that can be the cause for other complications such as multi-organ failure. It has also been obvious that high volumes could be linked to over distension and not necessarily pressure by itself. And it's interesting to note that PEEP was able to limit high volume-induced lung injury in some experimental studies. So I guess volume is a great determinant of VILI, yes.
So to start on volume, where are you coming from?
So yes, the question asked was, should we go beyond 6 to 8 meters per kilogram of predicted body weight? And if we go back to 1972, the recommendation was using very large tidal volumes from 10 to 15 meters per kilogram of actual body weight. And since then, there has been many improvements in first estimating the lung size of the patients by using predicted body weight. That was better than actual body weight. And predicted body weight, it's important to know that it's mainly influenced by the age and the sex of the patient. So using this approach of setting tidal volume using predicting body weight has improved clinical outcomes and especially mortality of patients with and without ARDS. And it has been, and it is known now from a long time, that setting the tidal volume to from 6 to 8 meters per kilogram of predicted body weight was better than 10 to 12 meters of predicted body weight. But there are shortcomings with this PBW approach. It has been shown that in the patients with the same sex, same height, and ventilated both with 6 meters per kilogram of tidal volumes, we could see, especially here on the left side on CT scan images, some signs of over-distension. And then the concept that the baby lung, that is the reduced lung size of patients, especially those with the ARDS, caused inspiratory pressures to be high sometimes because of the extensive lung disease itself, but sometimes also because they have a stiff chest wall. So P-plat or VT of 6-8 meters per kilogram predicted body weight were considered since then as pro-surrogates for the risk of overdistension. So a better physiological approach could be from this point to set tidal volume according to measures of aerated lung volume in order to scale to the aerated lung volume. So that's the concept that was used with this driving pressure. That is only the reflection of the size of the tidal volume related to aerated lung volume, and especially the compliance of the respiratory system. And when it was retrospectively assessed using in individual patient data by Amato and colleagues, it has been obvious that having a high driving pressure, possibly a threshold above 14 centimeters of water, was directly related to higher mortality. And in this study, what was interesting that tidal volume nor PEEP were not related to this risk of mortality. However, this approach has not been prospectively validated nor evaluated actually, so we don't know whether this could be an endpoint in itself. And the other limitation is that plateau pressure is the component of driving pressure is influenced by the chest wall. So how could we take into account the chest wall? There has been the lung stress, the interest in lung stress that is the force applied to the lung related to its surface area. And this can be estimated by measuring transpulmonary pressure at the difference between alveolar pressure and pleural pressure. And end inspiratory transpulmonary pressure may represent the highest level of stress to which the lung could be exposed. And this could be used as a marker of overdistension injury. And it has been proposed in some studies, some preliminary studies, that this threshold of 15 centimeters of water should not be we shouldn't go over this threshold. But there are also limitations to this approach because pleural pressure is estimated based on esophageal pressure, so it would require esophageal manometry. It would only estimate the global pleural pressure, not regional variations in pleural pressure. And there are no clear boundaries actually in humans for this parameter. A final approach, a recent approach, was also to look at the lung strain as a ratio of the stretch of the lung to its resting volume, which can be estimated, at least in its dynamic part, by the ratio between tidal volume and functional residual capacity, or end expiratory lung volume. And by doing so, it was obvious that patients with low volumes, patients with higher tidal volumes, but also patients with higher or lower levels of PEEP were exposed to the same amount of lung stress or lung strain. So again, suggesting that P-plat or a tidal volume on predicted body weight were not the best surrogates for overdistension. But again, there are many limitations for this approach. We don't know the thresholds for the safe strain. In healthy pigs using VTs from a range to 20 meters of kilogram. Only the dynamic lung strain, when it get above 1.5 or 2, then we could see some villi developing. But in ventilated patients with lung injury, then some authors could observe an inflammatory biological response starting from a strain of 0.27. This method would require a valid measurement of FRCE, and sometimes the ratio VT on FRCE may overestimate the strain because there is some recruitment in most patients during inspiration, and the VT, some of the VT is distributed to alveoli that open during inspiration, but other will stretch previously aerated alveoli, so it's not easy to manipulate. So what I would say in conclusion is that villi from overdistension can occur at tidal volumes and P-plats that are lower than those that are in current use in most ICUs, even for ARDS patients. But unfortunately, we have no reliable test for ongoing villi from overdistension. And we do not know, that's maybe the most important point, we do not know really safe levels for any of these parameters, even for tidal volume or P-plats. So much work needs to be done. And it's not very surprising that current recommendation, even in patients with most severe forms of lung injury with the ARDS, would propose actually currently to limit tidal volumes from a range from 4 to 8 meters per kilogram of predicted body weight, and limit inspiratory plateau pressures below 30 centimeters of water.
Thank you, Matthieu, for all these messages and all this explanation. I have a question from Germany, and the person asks, why should not using the lowered tidal volume for all severe patients? So why not 4 to 5 for everybody?
Well, it could be very interesting because at least we would have more chances to limit overdistension, and it's less risky to use unnecessarily low tidal volumes than unnecessarily high tidal volumes. That has been well shown by previous studies. But actually, there are some pitfalls of using low tidal volumes in patients, going from hypercapnic acidosis, atelic trauma risks. That is,
why atelic trauma?
Well, because we would have low pressure in some alveoli that would account for opening and closing injury of these alveoli, and atelic trauma would have the same effect almost than volotrauma actually, with also structural consequences, biological alterations, and villi actually. But we know for this risk that applying a certain amount of PEEP would prevent these side effects. So that could be manageable. But there are also pitfalls of using low tidal volumes. In some patients, it would cause or at least encourage the risk of dysynchrony and sometimes of double breathing, double triggering. That's something we should be aware of. Sometimes it would imply more sedation, more muscle paralysis in this patient, and that may not be a goal in itself in some patients. And then we have some tricks if we want to counterbalance this risk of lower tidal volumes, such as increase the respiratory rate, but we know now that it's also a contributor to VILI when we get these rates too high. And of course, we need to avoid unnecessary instrumental dead space, use humidifiers, etc. And ultimately, we would need some way to remove carbon dioxide that would not be eliminated by the lung.
Okay, so I understand that maybe we have to discuss together with Sam according to the pressure we put in the lung. Maybe Liz, what do you use in your ICU? And you agree with Matthieu? And how do you choose tidal volume for severe patient?
I totally agree with all the points mentioned by Matthieu. My point about that is the practical reality. Because even if we, of course, would like to ventilate all our ARDS patients with maximum 6 milliliter of ideal body weight, we very well see, as also demonstrated in the lung safe study from a general point of view, that at the bedside, we often have too high tidal volumes, even if we know that we should not. And this is probably one of my main message. We can do a lot of things to improve ventilation, but the first thing we can do to improve ventilation is to really apply what we know and what we know that is efficient. And probably in the future going to lower tidal volumes and also maybe use very early prone positioning when we have very low tidal volumes. It's a question, an open question.
Samir, something to say about that?
Yes, I agree what when you imagine that the future, Matthieu, I want to ask a question for Matthieu. Do you think that the future should be adapted for everybody a different tidal volume? Because today we said, I don't know, you said 4, 5, 6. We did not deliver to a patient the same antibiotic. Then probably we should adapt it. Do you think that the CT scan, I don't know, or other things like EIT and then, that could help to adapt for each patient the tidal volume according the injury showed by the CT scan? That means less you have aerated area, less tidal volume, and then what do you think about this approach for the future according your?
Yes, I guess it's a major question, and I guess it's why recommendations are so wide, from 4 to 8, even if ARDS, because we should adapt, we should individualize to each patient. Actually, many patients, and that's also what I guess Liz suggested, may tolerate well higher tidal volumes because they would not be responsible for high pressure, they have good lung compliance, and they would not be impact badly from this approach. But of course, in patients that are the most severe, we should better individualize. And at this time, it's true that using plateau pressure, for example, as a surrogate for overdistension may not be ideal. And we should at least try at the bedside to estimate lung volume, whatever the tool that is used. CT scan may be very performant, but we should transfer our patient to the imaging department, etc. So it's not very convenient at all times. EIT tomography electric impedance tomography is a very interesting and recent way to do this. But then we should check whether regional variations in aeration will represent a goal in themselves. But there are very recent papers that suggest it would be a very valuable tool to better individualize tidal volume.
Thank you, Matthieu. And we'll have 2 e-symposia between noon and 14, we will discuss a different way to assess lung volume, maybe at bedside today. I understand that you say that maybe PEEP is a way to decrease atelic trauma when we use low tidal volume.